So our previous video covered simple interest. That's the foundation of what we're going to really be studying in this section. So you've got simple interest where the interest is only earned on the original principal, the amount that you invest. Whereas compound interest, the interest is earned on the current balance of your account, right? So what that means is after a certain amount of time, the bank pays you interest and they deposit that interest into that savings account. And so the next time that you earn interest on the initial principal and you earn interest on the previous interest that you earned. And so what happens with that is you get this snowball effect. When you start earning interest on your interest, that starts building up and you have the potential of making more money using compound interest than you would with simple interest. All right, so compound interest definition, the interest that's computed on the principal plus any previous interest. Okay, so just a quick note on how this works. We can take a look at the formula that we saw in the last video of simple interest. Okay, so let's suppose that we invest $100 to make it easy with a 5% interest rate, and let's say that this interest is compounded annually. What that means is that the bank will deposit whatever interest that we earned each year. So at the end of year one, they're going to deposit some money. Then at the end of year two, they'll deposit more interest. And at the end of every year, right, it's compounded annually. So at the end of year one, we can calculate how much our accumulated amount will be, right, using that A equals P times 1 plus RT formula. Now this formula right here. Okay, where P is 100, R is 0.05, and T will be 1, right? Because we're calculating this at the end of year one, and each subsequent year will be T equal 1, because we're calculating the interest after each year. All right, so A equals 100 times 1 plus 0.05 times 1. That will give us an answer of 105, right? So at the end of year one, we'll earn $5 in interest plus the original $100. And then at the end of year two, the bank will give us interest on the current balance of $105. So we're earning interest on the $100, the initial principal, plus the $5 interest that we earned in the previous year. And so we can, again, use that formula to calculate how much we'll have in the account at the end of year two. A equals 105 times 1 plus 0.05 times 1. Let's give this $110.25. And then at the end of year three, we can calculate how much we'll have after the bank deposits the interest at the end of year three. 110.25 times 1 plus 1.05 times 1 gives us $115.76. Okay, notice that if this were a simple interest, we at the end of year two, we would just have the $110, right? So we're making an extra 25 cents with this compound interest. At the end of year three, we would have made $115 off of simple interest. All right, so now we've got an extra 76 cents that we're making with compound interest. Doesn't seem like a lot now, but we're only investing $100, and it will begin the snowball effect, right? The longer we keep that money in there, the more effect that compound interest will make on our accumulated amount. All right, but so we can summarize this over that 3-year period. What we're doing, right, all we're doing is we're multiplying this 100, the original principal, times 1 plus 0.05 times 1, 3 times, really is what we're doing, right? Because we multiply this, we get 105. Then we carry that 105 over to the next formula, multiply by 1 plus 0.05 again, and again. So to summarize that, to write as one line, we're multiplying 100 times 1.05 times 1.05 times 1.05 Or I can summarize that as 100 times 1.05 to the third power, right? I'm multiplying 1.05 3 times. And so we can summarize this into a formula as A equals P times 1 plus R to the T when it's compounded annually. Instead of having to calculate this 3 times or however many years that we're investing, we can summarize this using this formula. This is the compound interest formula for compounded annually. Now, if we're doing anything other than a compound annually, we need to adjust this formula. For example, we can compound annually, right? That means that we're going to deposit the interest once every year. There's also compound semi-annually, to where you deposit the interest twice a year. Compound quarterly, we'd be depositing the interest at the end of each quarter. There's 4 quarters in a year, so we deposit the interest 4 times in a year. Compounded monthly, 12 times in a year. Weekly, 52 times a year. And daily, 365 times a year. And so this M, right, that M, we're calling M the number of times that we deposit the interest over a year time. So this compound interest formula that we saw in the previous slide will be modified by dividing the rate by M and multiplying the time by M. So that way, this M times T is the number of compounds per year. In the previous case that we saw, it was compounded annually, so we only had 1 compound each year, so we could have just used the time, the 3 years. And then the rate divided by M, that is the interest rate per period. So we're dividing the rate by the number of periods that we have in each year. And we're letting, in the textbook, you'll see that they use I to represent R over M, and they use N to represent M over T. That should be an M times T right there. M times T. To make it a more condensed formula, A equals P times 1 plus I to the N power is our compound interest formula that we'll be using. Let's look at an example to see how this is going to work. All right, so 5.5 years ago, Chris invested $10,000 in a retirement fund that grew at the rate of 6.82% per year compounded quarterly. And what we want to determine is how much is the account worth today? In other words, we want to know the accumulated amount. How much is it worth today, the accumulated amount. So useful to identify our variables. How much did we invest? Chris invested $10,000. What was the interest rate? 6.82% or 0.0682, written as a decimal. Okay, what's the time? This was 5.5 years ago, so 5.5 years. And what is the compound? This is compound quarterly, right? So that means that M is equal to 4. There's 4 quarters in a year. All right, so once we identify the variable, then we can use this condensed formula. If you like using the longer version to where you don't have that I and the N, you can make the habit of using this formula with the M's. I like using this formula because it includes all of my variables. A is equal to P times 1 plus R over M raised to the M times T. And I know all my variables. P is 10,000. R is 0.0682. M is 4. And that's raised to the 4 times 5.5. And now I like writing it like this because I intend to put this into the calculator exactly as it's written. So that way I don't have any immediate answers that I need to calculate. All right, so let's take a look. I'm going to type it in exactly like I see it. Maybe one exception, you will need parentheses around the exponent if you're typing it in exactly as you see it there. All right, so we're going to begin by typing 10,000 parentheses 1 plus 0.0682 divided by 4. Being able to type this in as an entire fraction, an entire formula into the calculator all at once makes this process much, much easier instead of trying to perform each calculation throughout the formula. Just type it in all at once if you have that ability. So we're using the exponent, this caret key right here, raised to the parentheses 4 times 5.5. Okay, and we get an answer of 14505. That is $14,505. And now once you get to the final answer, you can round to 2 decimal places since we're talking about money, 0.43. So if Chris invested $10,000 5.5 years ago at a rate of 6.82% compounded quarterly, then his account will be worth $14,505.43. All right, so he made $4,505 in interest over that 5.5 years, which is a pretty good amount. All right, that's how we use that compound interest formula. We'll see some additional examples in the next video to where we're not just finding A, but we can use the formula to find the original principal. We can find the interest rate. We can also find the time.